Okay, so last week we talked about conditional expectation between two discrete random variables. So we will consider two jointly absolutely continuous random variables today. Okay, so we assume xy has a joint PDF f of xy. Okay, and we recall in chapter 6 that the conditional PDF of random variable x given that capital Y is equal to little y is defined as, okay, so we defined in here depends on that the marginal PDF of random variable y is positive at little y. In this case, then the conditional PDF of random variable x, given that random variable y equal to little y, is the ratio between these two PDF. Okay, so the numerator is the joint PDF of x and y, and the denominator denominator is the marginal PDF of random variable y, and okay, so that is the conditional PDF we defined before. Okay, so that's the conditional. So you can see that conditional PDF is a PDF. Okay, so so the conditional expectation. So we define of x given that random variable y is equal to little y is defined as okay, so it's defined as the following way. Okay, so the definition will be given in two cases. The first one so okay, so it's defined to be okay, it's defined by using the conditional PDF, all right, to find this integral. And it is clear that according to these two different cases, we have divided by and there is if the integral exists. Okay, so if the integral exists. For example, if if a random variable x has finite expectation, then of course, for each little y, such that the marginal PDF of random variable y at little y equal to 0, then this conditional expectation is, by definition, is equal to the unconditional expectation of x, so it exists. Okay. Okay, so that is the definition. And it can be shown that if random variable x has a finite expectation, then the conditional expectation of x given random variable y equal to little y exists and is finite. Okay, for all y in R. Okay, so it can be shown. Okay. And in this case, okay, in this case, the conditional expectation of a random variable x given that random variable y equal to little y all right, it's a real valued function of y on the whole real line, and can be denoted as gy, i.e. G that is a function from R to R. Okay, so it's from R to R. Now, the function g of y. Okay, so now we will use g as data processing function. Okay, to process y. Then gy of y can be shown to be a random variable, okay, and will be denoted as this symbol. Okay, so this symbol, the conditional, so we call it the conditional expectation of x given random variable y. Okay, given random variable y. Right. So this one is called the conditional expectation, all right, of x given y. And this is indeed, mathematically, it is a function y. And that function g is constructed by using this conditional expectation of x given that random variable y equal to little y. Okay. Okay, and so that's for an outcome omega in the sample space. We have that that the value of this random variable at this outcome, okay, so by definition this is actually, okay, and this is exactly equal to, okay, so we know. So up to now, you can see that x and y can be arbitrarily related, right? They can be arbitrarily. They may have correlation or uncorrelated or anything. Okay. So, but we always, so if they are, in this case, if they are jointly absolutely continuous, then we can, indeed, we can define a random variable, okay? And such a random variable contains information about the conditional expectation of random variable x given that random variable y equal to little y. It contains this information, okay? And so that this construction, okay, enable the following theorem. So this is theorem 7.5.1 in the case of absolute continuity. Okay, so x, y are two jointly absolutely continuous random variables, okay, with a joint PDF f of x, y, okay. So now if x has a finite expectation, then then its expectation can be computed in 2 steps. First of all, you can compute the conditional expectation of a random variable x given random variable y. Okay, so that is the a function y, and such a function g is actually this one, and this one should be computed in terms of the conditional PDF of random variable x given random variable y. Okay, in this formula to compute. Okay, and so that would be, because this is a function of y, so the expectation is y. Okay. All right. So instead of course, you can, if you are able to evaluate. So of course, this is the ordinary way to find the expectation of x, right? So from the drawn PDF, you find the marginal PDF of random variable x and evaluate this integral to find the expectation of x. This is one way. But if this way is difficult, or by the nature of the problem, you are able to find the marginal PDF of random variable y, as well as you can find the conditional expectation of random variable x given that random variable y equal to little y through some easily obtained conditional PDF of random variable x given random variable y. Okay, so in many practical situations, you are given this conditional PDF naturally, and so it will enable you to find the conditional expectation of random variable x given random variable y equal to y. Okay, all right. So this proposition provides you an alternative method to find the conditional expectation of x in a 2-step way. Okay. Any questions before we move to the proof of this proposition? No, good. So let's see a proof. Okay, so now we compute the expectation of this random variable. Okay, and so we know this is G, and so that would be okay. And we can evaluate over y such that the marginal PDF is positive at the rows y. In this situation, now this one can be replaced by this formula. So we have okay, so we can cancel them. Okay, and then we move here. So we have y oh, I forgot to put the differential dx here. Y here. Now we can include all y, not just y, such that this marginal PDF of random value y is positive. Okay, so okay, since for such little y, for little y such that this marginal PDF is 0, and we know, okay, so that this integral is 0. And this implies that f of y is this for almost all x in R. Okay. And this implies that x times f of xy equal to 0 for almost all x in R. So this implies that okay. So if we include rows y such that the marginal PDF of random value y is 0, then the added part. So maybe I okay. So maybe I add this part. Okay. Because all this they are all zeros, okay? So the integrand is always 0, okay? By this explanation here. So that when we combine together, okay? So we have that. And now we will exchange the order of integration. Okay. Since the order of integration is exchangeable, for the expectation of x, it's okay, because when x has finite expectation, then the absolute value of x also has finite expectation. Okay. But this expectation is actually here. So if we take, so that means that the integrand, when we take the absolute value of the integrand, the integral is always finite. In this case, then the order of integration is exchangeable. Okay, so that means the absolute integrability implies the integrability. Okay, and so that is the it's from this factor that this order of integration is exchangeable. Okay, and so this is and we have done. Okay. Okay, now so let's take an example. So we take an example here, and 75F. Now, two jointly, absolutely continuous random variables x and y are said to be jointly normal. Okay, if they have a joint PDF. Okay, so if they have the joint PDF in the following form, it's a 2 pi sigma x sigma y square root of 1 minus rho square. Okay, and the exponential function. All right, so the exponent term is a little bit complicated. Rho square of x minus eta x square and a sigma x square minus 2 rho x minus eta x y minus eta capital Y divided by sigma x sigma y plus y minus eta capital Y square divided by sigma y square. Okay, it's good. Okay. So the joint PDF is an exponential function. And you can see there are 5 parameters for this joint PDF. One is eta capital X, eta capital Y, rho, right? And sigma X. You can say sigma X square and sigma Y square. So there are 5 parameters to describe this spatial kind of PDF. Okay. Okay. This joint PDF, which is usually called a joint normal probability density function. Okay? A joint normal PDF. Which is specified by 5 parameters. Mu x, oh, I use eta. Okay, eta. Okay, eta x, eta y, rho sigma x square, sigma y square. Okay. Now, the marginal PDFs are, so now we can compute the marginal PDFs, right? Now for x, okay, so when you do the integration, then you will find that because we are doing this, so that we have square root 2 pi sigma x square, okay, and exponential minus x minus eta x divided by 2. Okay. Okay. Well, you can actually, if you do it 2 pi sigma y square 1 minus rho square, and you have exponential minus y minus eta y I think 1 over 2 sigma y square 1 minus rho square, and y minus eta y plus rho sigma y divided by sigma x, and x minus eta x the square and the dy. Okay, so you have to split because that we integrate over dy, right? So this part, some part of that can be moved out. Okay, and so in here you can see that it's a normal PDF, right? The variance is the sigma y square times 1 minus rho square, right? And the mean will be this number. This is the mean. Okay, so you can see that. So after so that the integral is equal to 1. because it's so this one a normal PDF with mean y plus rho x okay, and variance sigma y square y minus r square. Okay. So that the integral is equal to 1. Okay, so this has become 2 pi sigma square, sigma x square e to the okay, so which is a normal PDF with mean eta x and the variance sigma x square. Okay, so the parameter, this parameter eta x is just the expectation of random variable x, and the sigma sub x square is just the variance of the random variable capital X. Okay? So you know the meaning of these two parameters. Okay. And similarly, we can find the marginal PDF. Exponential function of okay, so now we can integrate, and the integrand here again is a normal PDF with mean eta x plus rho sigma x sigma y y minus eta y, and variance sigma x square times 1 minus rho square. Okay, so when we integrate this normal PDF over the whole range of the real line is equal to 1, right? So this is 2 pi okay. So once again, which is a normal PDF with mean eta y and the variance sigma y square. Okay, so now we know the meaning of 4 parameters out of 5 parameters. So we know eta x is the expectation of random variable x. Eta y is the expectation of random variable y. Sigma x square is the variance of random variable x. And sigma y square is the variance of random variable capital Y. Now, so it remains rho. What is the meaning of rho, right? Yeah. Right. What is the meaning of this parameter rho? Any questions before I proceed? All right, so we conclude that that's x and y are normal random variables. So when x and y are jointly normal, okay, so when 2 random variables are jointly normal, right, means that they are jointly absolutely continuous with such a joint PDF. Okay, so this joint PDF is called joint normal PDF. Okay, and then x and y are normal random variables. Okay, they are random variables with mean eta x variance of x sigma x square. Mean of y is eta y, and the variance of y is sigma y square. We now show that rho is the correlation coefficient between x and y. Okay, so now I will show the last parameter rho is the correlation coefficient between x and y. The correlation coefficient between x and y, it's, so by definition, it's here, is the covariance of x and y, and the square root of variance of x, variance of y. Okay? And so now we know what is the variance of x and variance of y, right? So this is sigma x and sigma y, because we take the square root. And the covariance of xy is actually the correlation of x and y minus the product of their means. Okay. So to find the correlation coefficient, we need to compute this expectation. Of course, you can evaluate. Of course, you can evaluate here. You can evaluate this expectation directly, right? Okay. So you can evaluate it directly. But when you look at the joint normal PDF, you can see here, it's really complicated, right? All right, but still doable. You can do it directly, okay? But instead, we will do it, we will apply conditional expectation instead of computing EXY directly as okay, we will find so we will find this expectation in 2 steps. Okay, so we will find in 2 steps. So we will find the conditional expectation of x times y, given random variable y. So we will compute it. All right. Now, to compute, this condition expectation. So this is compute condition expectation, as we know, and we know that the marginal PDF of y is normal. So normal PDF never 0, right? Because it's exponential function. So normal PDF never 0, right? Never 0. Okay, so this one would be what? Should be x and y. So that would be So that because y, we already know. Oh, I forgot to. Okay. Mm-hmm. Okay. So I need a lemma. Lemma. So this lemma is called 7.5. I think I had. Okay. Okay. All right. The lemma state that x, y jointly, absolutely continuous with a joint PDF okay, and the G piecewise continuous real valued function on R. Okay. Now if x has a finite expectation and x times g of y has a finite expectation, then the conditional expectation of x times gy given y is equal to gy with and then expectation of x gy is equal to with probability 1. Okay. And actually, this is an exercise in the textbook. Okay, and so last night I just ask you to prove it when x and y are discrete random variables, right? Okay, so anyway, and this is the same. if x and y are jointly absolutely continuous. Okay, so if x and y are jointly absolutely continuous with the joint PDF, G is a piecewise continuous real value functions. This ensures that the G of y is a random variable. Okay, and if x has a finite expectation, and x times gy has a finite expectation. Okay, if both of them have finite expectation, then for all y such that the marginal PDF is positive at this little y, then we have this relationship. Okay, so basically it says that because you are given that the random variable is equal to little y, so that this is already determined because capital Y is little y. So this is a constant, so you can move it out, basically. Right? Because you already know the information of capital Y. So now you can, so when you know this is Gy, and you can move it out because it's a constant. And you have that. Okay, so you have this identity. And so by using the random variable version, so that means that the conditional expectation of this product given random variable y is the product of two random variables. One is random variable G of y and random variable G of and times the conditional expectation of random variable x given random variable y. Okay, so this is a function of y. Okay, this is also a function of y. Okay, and also this is a function of y again. So we have, and with v1 it is because that because for little y such that fy of y equal to 0, this equality may not be true. Okay, may not be true, but they occur with probability 0. Okay. Okay, and so the proof as an exercise. Okay. So this will be an exercise for you. Yes. Equal to 0. Oh, okay. Because that because this one is a function. Maybe G is not a good symbol. Probably don't use G. Otherwise you are confused. H. Okay. Good. Okay. Now, all right. So let me. That is a very good question. So let me explain the meaning of this. Okay. as before, G of y is the conditional expectation of random variable x given that random variable y is equal to d to y. And the f of y defined to be now this is the condition, the expectation of this random variable. The new random variable is x times h times y. You can think about this as z, right? Random variable is z. Okay. So again, it's a function of y. It's a function of y. Okay. Okay. And we say that they are equal with probability 1. Right. So now define this one. Okay. So that so expectation then expectation of x given y is g of y, and expectation of x h y is f of y. Okay, good. Now, so let omega 0 to be all the outcome such that fy so I have to say, okay, I will omega 0 to be inverse of okay, so the inverse mapping. Okay. Oh, no. I have to say okay, all right. So a region, an interval. So I was use a notation. Let me see. Okay, J to be all such that. Okay. All right. So it is the is the set of all y such that the PDF of random variable y is positive at little y. Okay. Then we know that it's equal to 1. Okay. So that is this is such that okay. So this integral okay, so with this probability density function y, that, that when we integrate over all the j, it's equal to 1. Okay? Okay. But, and for all y in j, right, we have and then we have this one, right? And then we have E of x h is equal to h of y, and okay, and this is actually equal to f of y, and this is equal to h of y and the g of y. Okay, so you can see that for all y in this set J, that they are equal, right? Fy is equal to hy times gy. So that is the meaning. Okay, so this is true for all y in J. But when you integrate over the y in J through this probability density function, the probability is 1. Okay. So that the reason is here, in between here, because they are equal for all y with the marginal PDF of random variable y is positive. Then it is possible that if y is not in J, then these two functions are not equal. It's possible. Okay, so if little y is not in J, then f of y may not be equal to the product of hy and gy. Why? The reason is the expectation. If by our definition, if a marginal PDF of capital Y is 0 at Y, then by definition, this is the expectation. Okay. And now for y not equal to j, i.e. we have Okay. Now this may not be equal to that, because the expectation of x times this random variable may not be equal to the expectation of x times hy. Why? Because hy basically depends on y, right? But this one is a constant. This is a constant. So if there are many y such that f of y is 0, then some of the y may not be equal. By our definition, because we define, in this case, we define this conditional expectation to be the expectation, the unconditional expectation of this one. And similarly here, the conditional expectation becomes the unconditional one if f sub y of little y is 0. It's from our definition. Okay? So though they may not be equal, and quite often they are not equal. The reason is this is constant. This is constant. But this is changing, right? It's a function of little y. So when y changed, unless it's a constant function, right? And equal to the ratio of these two expectations, right? Unless. But that is very special. Okay? That is very special because here h can be arbitrary. You see here in this lemma, h is a piecewise continuous real value function, so it can be arbitrary. Okay, so this is the normal case is that they are not equal. Okay, but for those y, the probability density function at such little y is 0. All right, so they will occur with probability 0. Okay, so that's why we will say here. Okay, so this is exactly the same as the previous one. They are the same. Okay, they are the same. Because this is in terms of the function. Okay, and this is in terms of random variable. As a function of y. Okay, as a function of y. As a function of y, then they were equal with probability 1. Okay. Any further question? So this is a general factor you can use. Okay, a general factor in the use. Okay. Okay, and so we now back to our example. Okay, so now expectation of xy given y, okay, is equal to y expectation of x given y. With probability 1. Okay, so two random variables are equal with probability 1. Means that basically they are equal, right? Because in probability theory, if two random variables are equal with probability 1, then they will have the same distribution. Okay, they have the same cumulative distribution function, so they have the same PCDF. And so if they are absolute continuous, then they have the same PDF. They can choose the same PDF for them. Okay, all right. So we have this with probability 1. Okay, so that what we need is to compute the conditional expectation of x given y. This is really we need, right? Okay, so to find it, then the conditional the conditional PDF of x given that y equal y is actually it's f of x given y is actually which y? This one. This one. Why? Well, you know that basically this right? Because the marginal PDF of random variable y always positive. So that we can define. So this is actually okay. So this is always true. The reason is the marginal PDF of y is normal, and the normal PDF always positive for over the whole real line. So they are positive. Okay, so that this is the ratio. Okay, and so you can see the f of xy is the product of marginal PDF and this one. And from here, from our integration, you see that, so we now go back to see it. This is already, we already know this is what? This is equal to the marginal PDF. So you can think about this normal PDF actually is equal to what? Is the conditional PDF of x given y. Right? Can you see that? Because if this is the case, then right. So if you replace the joint PDF by the product of the marginal PDF of y and the conditional PDF of x given y equal to y, so that the whole thing, so this becomes true. Because this is dependent on y, right? So you can move it out. Y. And this is the PDF. So that this is equal to 1. So when we look at that, you find the integrand itself. The integrand, right? It's just so that the integrand is just the conditional PDF of random variable x given y. Okay? So the conditional PDF is just, right? And which is a normal PDF with mean. And so the mean, you can see the mean is the sum of the mean of the random variable x plus a term. right? Determined by what? By the y, the given y, little y. Okay? And the variance sigma x squared times 1 minus 0 squared. So it's a normal PDF of this. And so immediately, so that's, we have the conditional expectation. The conditional expectation of random variable x given random variable y equal to little y is just the expectation of this conditional PDF, right? Which is normal. So that is this one. Immediately we have right down here. Okay. We don't need to compute it, right? We just look at to identify it's a normal PDF. Then we already know what is the mean, right? So the mean is this one. Okay, so which is an affine function, or linear function, you can say. It's a linear function of little y. Okay, so it's a linear function of little y. Any questions up to here? Okay, and then so that conditional expectation of random variable x given random variable y, which is just g of y. So this is this one is g of y, little y here, right? And g of y is a linear function of y. So that this is a constant plus sigma x divided by sigma y, capital Y minus eta y. Okay, it's this one. Okay? All right, so now expectation of xy given y becomes y expectation of, and so, and from here you can see that they are equal exactly everywhere, because not necessarily with probability 1. Why? Because the marginal PDF of y is positive always, right? Okay, so they are equal. Okay, exactly for every y. Okay, and so we put into here, we have eta xy plus sigma x sigma y y squared minus eta y y here. And then the expectation of xy is the expectation of xy given y. So that is expectation of eta x y plus sigma x sigma y plus minus sigma x sigma y times eta y here. Okay? Okay, and so bilinearity of, so we have oh, maybe I row, oh, okay. Oh, row here, okay. Thank you. Okay. Row of, okay. So plus rho sigma x y, and okay, this one, and eta x, eta y, okay, plus rho sigma x, sigma y. So this is the second moment minus the square of the mean, so that is the variance. And so this is eta x and this is variance, so this is square. Okay, so this is plus rho sigma x sigma y. Okay, so that is the final. And then we go back to, now we are able to find the correlation coefficients here. Okay. So now rho of xy, which is equal to expectation of xy minus eta x, eta y, divided by sigma x times sigma y. So this is equal to eta x, eta y, plus rho sigma x, sigma y, and minus eta x, eta y, sigma x, sigma y, and which is rho. And we have done, right? So rho is just the correlation coefficient. Okay. Okay. So from this example, we illustrate quite a few techniques, right? We learned up to now. Okay. Any questions? Okay. This example, will be further studied in the last section of this chapter. Okay. And the expression of the joint, the normal PDF, looks ugly, right? You see a lot of parameters there. And but we will have a nice looking formula for the expression of this joint PDF. When you have more than 2 random values which are jointly normal. Okay, so we will consider, for example, you have 1,000 random values, they are jointly normal. How can you write down a joint PDF for this 1,000 random variables? Okay, we can do so, all right, by the aid of linear algebra. Okay, so we will see that in the last section. And from our discussion, we know that for this PDF to be meaningful, we must put some restrictions on the parameters. First of all, the correlation coefficient should be in between 1 and -1, right? We know the correlation coefficient has absolute value less than or equal to 1. We already know, but they cannot be equal. Rho cannot be equal to 1 or -1. Why? Because if this is the case, then this is 0 and meaningless. Okay. Right. And second, the variance should be greater than 0. All right. Otherwise, you cannot put into the denominator. But the means can be any real numbers. Okay. So there are no restrictions for eta x, eta y. Okay. There can be any real numbers, and the rho should be in between 1 and the -1, but cannot equal to their ends. And the variance should be positive. Okay, so this is the restriction about the 5 parameters. Okay, to have such a joint normal PDF. Okay. Okay. Any questions? Great. All right. So now for the discussion of conditional expectation of a random variable given another random variable, we discussed 2 cases. For both of them to be discrete, or both of them are jointly absolutely, x and y are just these 2 random variables are jointly absolutely continuous. But we have 2 more, right? 2 more cases to study, because compared with the 4 cases we studied in chapter 6. Okay. Okay, so now recall that a random variable x, right, is called conditionally absolutely continuous given a discrete random variable n if, all right, if for each little n such that the event that capital N equal little n occur with positive probability, there exists, okay, a non-negative and integrable function. All right, this function will be denoted as f of sub x, capital X given capital Y, capital N, of little x given little n, on the real line such that the conditional CDF defined to be the probability that x is less than equal to little x and capital N equal to little n. Okay. So the conditional CDF, this condition always exists, right? Because this is a traditional conditional probability, all right? So this is actually the traditional conditional probability because that the denominator is positive of x given the event n equal to n can be expressed as an integral. So if okay. So we defined that before, right? So we say a random variable is conditionally absolutely continuous given a discrete random variable. Okay. So of course this random variable x must be continuous. Okay. Okay, and so we have this one. Okay. And also we call this function as the conditional PDF of x given that capital N equal to n. Okay, so this is. So suppose for each little n such that this probability is positive, then there exists a conditional PDF of x. All right, such a PDF, such that the conditional CDF can be expressed as the integration of this non-negative and integrable function. Okay. So it's a strong condition. So this is the case we discussed in chapter 6. Now, in this case, x is absolutely continuous. All right, with the PDF. So we can compute a PDF for random variable x. So that would be a weighted sum of the conditional PDF of random variable x given that random variable n equal to little n. Right, so we can find this one. If x and n are independent, the conditional CDF of x given the event n equal to n becomes, okay, so the condition becomes okay, because when they are independent, the joint probability becomes to the product of their respective probability. Okay, so this is become to the unconditional. All right, so it becomes to the unconditional PMF, CDF there. So that a conditional PDF of x given that n equal to little n is f equal to the unconditional one for all n such that probability greater than 0. Okay? Okay. And as we know, for convenience, for n such that probability is 0, we define the okay. So we define that the conditional PDF of random variable x given that capital N equal to n to be the unconditional PDF of x. As we know, this unconditional PDF exists over there, right? Right. So we will define this way. Okay, now so now the conditional expectation of x given that capital N equal to little n is defined as the integration of this sum. Okay, and so this becomes two cases that depends on whether this probability is positive or zero. Okay, so now for so you can evaluate them. So you still need the given conditional PDF and here provided that the integral exists. Okay, so it's here. And we will assume that the expectation of it exists and is finite. For all n such that 0. Well, maybe I will give. So if maybe I use the same argument, if x has a finite expectation, all right? If x has a finite expectation, then it can be shown that the conditional expectation of x given that n equal to n exists and is finite for all n such that the proof is similar to the one I gave for the case that x and y are discrete. Okay. You can just use that. maybe maybe I show it right here. Then its existence is finite. Okay. Okay. Expectation of x is finite. If and only if the expectation of finite. Okay. All right. So now we look at that expectation of the absolute value of x is equal to so this is, and by plug into this one, okay, and everything is non-negative, so we can exchange the order of integration. Okay. All right, and this is finite. Okay, and so this implies that this integration okay should be finite for all n such that probability is positive. Why? Because if for some little n this is positive and this is infinite, and infinite number, infinite times positive number is infinite again, so the sum become infinite. It's a contradiction. Okay, so this sum is finite, implies that if this probability is positive, then this integral should be finite. Okay, and absolute integrability implies that exists and is finite for all n such that and what is that? This is actually the expectation of x. Okay, so this shows that if x has finite expectation, then this conditional expectation exists and is finite for all n such that this probability is positive. Okay. Okay. And if this probability is 0, if this probability is 0, then by definition, the conditional expectation is equal to the unconditional one. But the unconditional one has been assumed to be finite, right? Yeah. So we have no problem with that. Okay. Now, if x and n are independent, and x has a finite expectation, then okay, then expectation of equal to then let me see. Okay, so here, if x and n are independent, and so we know we have this one. Okay. So if and x has a finite expectation, then expectation of by definition and this is true. Okay. Right? From this two you can see that the conditional PDF becomes to the unconditional one. Okay, belong here. And this is already by definition. Okay, when this probability is 0. Okay, and this is from the independence property when this probability is positive. Okay, so we have that, and this is EX. Okay, so if x and n are independent and x has finite expectation, then the conditional expectation of given that capital N equal to little n is the unconditional one for all n. Okay, this is what we know. And then position 7.5.1 AC to D. Okay, the case. So let n discrete. So now let x be conditionally absolutely continuous random variable given a discrete random variable capital N. If x has a finite expectation, then the expectation of x can be computed in 2 steps. The first, we compute, oh, I forgot to define the that's why, which is equal to summation okay, proof. All right, since x has a finite expectation, the conditional expectation of x given random variable n equal to little n exists and is finite. Okay? For all possible value n of n, right? And define a function g of n on R as follows: Gn to be expectation of x if n is a possible value of capital N and 0 otherwise. Okay, so we define a function. Okay, almost all n is 0, but g of n may be non-zero when little n is a possible value of capital N. Okay. All right, so then g of n is a discrete random variable. Okay, so when we composite, so we use g as the data processing function to process capital N, then we have a discrete random variable. And will be denoted as expectation of x given n. The conditional expectation of x given n. And for all omega in the sample space, G okay, right? So I put the definition into the proof. Okay. Now, the expectation of the conditional expectation of random variable x given random variable n, which is expectation of g of n. So this is because g of n is a function of n, so we have gn probability that n equal to n, right? So it's a function of capital N. Okay, and we've so from our definition, so this is condition expectation of x given capital N equal to n. Okay, so that this is a summation of n integration x f and the dx, and this one we can put into by using the PMF of capital N. Okay, so this is equal to this one. Now, we can exchange the order of the countable sum and the integration, right? Maybe I don't need to put the okay here. Since we have computer where since this one is it's finite. Okay, since the compute this is equal to okay, because this is finite, so we can exchange again. So if that we can do it absolutely, then the original integration can exchange the order of two limiting process, because integration is a limiting process, and the countable sum is also a limiting process. If you have a countably infinite many terms here. Okay, so you have that. Okay, and so this is x, and this is our definition. So this is and then we have done. Okay. So once again, we have similar results for this mixed type conditioning. X is continuous time random variable. The n is discrete. Okay. And here we assume that X is conditionally absolutely continuous given discrete random variable capital N. So in this case, we still have the two-step result, so that we are able to compute the expectation of a random variable X in terms of this formula, okay? In terms of this formula. Any questions? Okay. All right, and I forgot to say about a reminder. I forgot to mention that if X and Y are independent and absolutely continuous random variables with PDFs f of xx and f of y. Okay. So maybe let x and y be independent and absolute continuous, right? Okay. Now, if x has a finite expectation, then the conditional expectation of x given random variable y equal little y is equal to the unconditional y for all y. Okay. And proof as an exercise. Okay. So some easy things to see. Okay. I forgot to mention this. Okay. All right. So any questions? All right. So I think I have to stop here. And as the university has announced that the whole university will have the remote learning for 2 weeks from tomorrow to May 24th. Okay? So that you can't come here on Thursday. Okay, even though that would be my last in-person lecture. But you come here, you cannot. So, but we will do the live broadcast. So you can watch my YouTube channel at home or in your dormitory, okay, in the same class time, okay, on Thursday, okay. And for the next 2 weeks, I have already pre-recorded my lectures, so you can again watch my YouTube channel in the same class time. Maybe it's longer than the usual time, okay? Because because I forgot the time. Oh, I continue to lecture my material. So some of the lecture will be more than what you expect. Well, but you can take time, you know. Okay. Okay, and so, and I hope, okay, the next 2 quiz will be in the remote learning period. So I have asked TA to make an announcement for you how to do the quiz remote. All right, so please follow the instructions. And our final day is May 31st. I hope you will be able to come back to the campus, so we can do that in person. But if not, well, there will be. So again, so if not, then we should do it online. Okay, and so again, so please follow the instruction from TA. So they will ask you to have a good conduct in doing your final examination. But anyway, if you have any requests, send an email to me or to TA. Let us know if you have any difficulty. Okay? All right. So thank you very much to attend my class in this semester. It's a short semester, but densely, you know, I believe. Yeah, but anyway, thank you very much, because your presence here is a huge encouragement to me. Thank you.